Rehan Kasak, do this. Topic is very important. इसमें आप कुछ नहीं सुन पाओगे. Today we are going to discuss the electrophilic nucleosubstitution reactions of haloarenes. This is a very important topic. Important both for your 12th board exams as well as for your NEET and JEE preparation. हाँ ऑफ करके Today we are going to discuss electrophilic substitution reactions of haloarenes. Now, as you know that haloalkanes show mainly nucleophilic substitution reaction. What is the meaning of saying that? That haloalkanes show characteristic reactions as nucleophilic substitution reactions. But haloarenes do not do so. They show electrophilic substitution reactions as their characteristic reaction. Now, what is the reason behind that? First question is, why do haloarenes not show nucleophilic substitution reactions but show electrophilic substitution reactions? Reason: in science, in chemistry, there is nothing without the reason. If there is any assumption, then there must be some reason. Okay? So first we will discuss that why don't haloarenes show nucleophilic substitution reaction. This we will understand with the example of chlorobenzene. इसके कोई वायर वायर Nucleophilic reactions are not shown by haloarenes. Now the question is, why? The reason lies behind the resonating structures of haloarenes. We will take example of chlorobenzene. In chlorobenzene, the benzene ring contains 3 pairs of pi electrons. 3 pairs of pi electrons. And chlorine has 3 lone pairs. Now, one of these pairs is donated to the adjacent carbon atom, which is bonded with the chlorine, and a double bond is formed between that carbon and chlorine. A double bond is formed. Now, what will be the effect of this transfer of electrons? A double bond between carbon and chlorine. Now, 2 lone pairs only are there, and as chlorine has used its lone pair to form this pi bond, there will be a positive charge over chlorine. Now, as this carbon is already formed a double bond, this double bond is not required now. So these pi electrons will be shifted to the adjacent carbon, means here. So this carbon will acquire a negative charge. Now, double bonds in the ring. One double bond is already broken. Now there will be only 2 double bonds. This carbon cannot make double bond because already one is there, and this carbon has lone pair, so this also cannot be involved in the pi bond formation. So these and these carbons will form pi bonds. Again, this lone pair of electrons will be shifted to the next carbon, and as a result, these pi electrons will be shifted to adjacent carbon to it. Result, here it will remain same, 2 lone pairs and a positive charge. Lone pair is shifted now at this carbon, so negative charge will also shift to this carbon. These 2 carbons will not form pi bonds now inside the ring, so pi bonds will be there between these 2 carbons and these 2 carbons. Now all the carbons, please check in the resonating structure of arenes, means aromatic compounds, that each carbon should have either pi bond or lone pair of electrons. Again, this shifting will be continued in the same way. Now, lone pair is shifted to this carbon. Also, negative charge is shifted to this carbon. Now, double bond. These two carbons will not form double bonds. So, double bonds will be there between these two carbon atoms and these two carbon atoms. Again, now this carbon has got this lone pair back. So, now the double bond will be formed between these two carbons, and this pair of pi electrons will be returned back to the chlorine. Now there will be a single bond between carbon and chlorine. Again, there will be three pairs of electrons. Double bonds are now between these two carbons and these two carbons. Okay. These are the resonating structures of chlorobenzene. Now, if we name these structure, if we number these structure as first, second, third, fourth, and fifth. In the structure second, third, and fourth, there is a double bond between carbon and chlorine. So we can say that chlorobenzene has a partial double bond character between carbon and chlorine. In chlorobenzene, there is a partial double bond character between carbon and chlorine due to the resonance. Therefore, haloarenes do not exhibit nucleophilic substitution reactions because now the removal of chlorine will be difficult. We can write this. Now the question, second question, why do haloarenes show electrophilic substitution reactions?
Reason is again in the resonating structures. In these three resonating structures, as you can see, the electron density is higher either at ortho position or at para position. Either ortho position or para position. Okay? Electron density is increased in haloarenes. Already, benzene ring is an electron-rich subspecies. Electron-rich species due to the presence of 3 pi electron pairs. Due to the presence of 3 pairs of pi electrons, benzene ring, or we can say aromatic rings, are electron-rich species. And what is a nucleophile? Or what is an electrophile? You know that nucleophile are electron-rich species and electrophiles are the electron deficient, means electron-seeking species. They are looking for electrons. So electrophiles easily attack on this electron-rich benzene ring, and therefore electrophilic substitution reactions take place. Now, one more question is there. Why haloarenes, in case of haloarenes, the nucleophile attacks either on the ortho position or para positions. Meta derivatives are not formed in the electrophilic substitution reactions of haloarenes. Reason, as I told you, that in these three resonating structures, electron density is higher either at ortho position or at para position. And electrophile is an electron seeking species. It is looking for electrons. So where will it attack? It will attack either at the ortho position or para position. So during the electrophilic substitution reactions of haloarenes, ortho and para derivatives are formed, but meta derivatives are not formed. This is the one point. Now when we compare between ortho and para derivatives, the para derivatives are the major products and ortho derivatives are the minor products. The reason? Symmetry. Reason is symmetry. Due to the symmetry, para derivatives are more stable. As para derivatives are more stable, they are formed as major products, and ortho derivatives are formed as minor products. Approximate 80-20% ratio is there. 80% is the para derivative and 20% is the ortho derivative. Now we will discuss some examples of electrophilic substitution reactions. First, we can take halogenation, means substitution by halogen group. We can form benzene ring in this form. One chlorine is already there. We will take halogen directly. Now, in these reactions, the catalyst which is used is either anhydrous aluminum chloride or anhydrous ferric chloride, AlCl3 or FeCl3. This one is 1,4-dichlorobenzene in IUPAC system and ortho-dichlorobenzene in common system. Sorry, this one is para and this one is ortho. Dichlorobenzene. Now, you can see these both have two pairs of electrons, two pairs of lone pair they have. Now these chlorines are close to each other. They will repel. These electron pairs will repel each other, which will decrease the stability. Here, these chlorines are far from each other. They are at maximum distance. So there is a very less chance of the repulsion between the electron pairs of these two chlorines. That's why para derivative is more stable than the ortho one. So I hope now you know the reason. You have understood the reason that why para derivatives are the major products. There will be removal of HCl. And please do take care. Don't try to balance these reactions. If you will write 2 here, then it will become wrong. It will be wrong because from 1 mole of this chlorobenzene, approximate 80% is converted into para derivative and 20% is converted into ortho derivative. This 1 mole is divided in different ratio. If you will try to balance it, if you write 2 here, then it will mean that equal amount of both the products are formed, which will be wrong. Alright, second reaction we will take. Sulfonation means addition of sulfonate group reaction will be done with sulfuric acid. Now I can write this sulfuric acid in a different form. This is also sulfuric acid. We can write sulfuric acid in this form also, H2SO4. Why I have written in this form? Because only this group will substitute hydrogen from the benzene ring. Okay. Any catalyst is not required in this reaction as sulfuric acid itself highly reactive. And we take dilute sulfuric acid . Same para and ortho derivatives will be performed approximately in the same ratio, 80-20% as in the previous reaction. Alright, what will be the name of this compound? IUPAC name? Four-chloro benzene sulfonic acid. This one will be 2-chlorobenzene sulfonic acid. The difference in the name only in the position of the substituent group, where the sulfonic group is added. According to that, we mention the position. Rest of the name will remain same. Same major, minor. Now third reaction we will take nitration. Means addition of nitro group. And also remember that in the previous reaction, the removing group, the group which will be eliminated is water. Nitric acid, HNO3. I have written in this form. Now you know why. Because this OH will be removed along with the hydrogen of benzene ring and water will be formed, and this NO2 group, nitro group will be combined, will be attached to the benzene ring. The reaction will be done in the presence of sulfuric acid, because if sulfuric acid will not be used, then all the ortho para hydrogens will be substituted by the nitro group. If we want mono nitro derivative, then we have to use sulfuric acid to control the reaction. One chloro, 4 nitro benzene. Here chlorine and nitro group both are used in prefixes. As both are used in prefix, so alphabetical order will be followed. We will follow the alphabetical order. C comes first, then the N. So first we will write chloro and then we will write nitro. And this one 1 chloro, 2 nitro benzene. Okay. Reaction will be completed with the removal of water molecule. All right. Now next we will take Radial-Crafts reaction. This reaction is done in two different manner. Two different reactions are there. One is called Radial-Craft alkylation, in which alkyl group will be get attached to the benzene ring, and the reaction is done with any haloalkane. Radial-Crafts reaction is always done in the presence of anhydrous aluminum chloride or anhydrous ferric chloride, that is FeCl3. Products, same para and ortho derivatives, in which para will be the major and ortho will be the minor. Name para-chlorotoluene, as if CH3 group is attached with benzene ring, it is called toluene. So para-chlorotoluene and orthochlorotoluenes, these will be the major products. Removing group is HCl. Second is Radial-Crafts acylation. This group is called acyl group, COCH3, where one valency of the carbon is free. For this reaction, we can take two different reagents. One, we can take CH3 C double bond OCl, or you can simply write CH3COCl, which is ethynyl chloride. Ethynyl chloride. Catalyst will remain same. This will be the major product, and this is the minor product. 4-chloroacetophenone and 2-chloroacetophenone. These are the IUPAC names. In common names, you can write para-chloroacetophenone and orthochloroacetophenone. Removing group CH3 COOH. Sorry, removing group here will be HCl. This reaction can be done in one more way. One more reagent can be taken, that is ethanoic anhydride. This one is ethanoic anhydride. Two molecules of ethanoic acid combined together with the removal of one water molecule. Okay. The products will remain same, byproducts will be different. Byproduct will be ethanoic acid this time. So these were the major electrophilic substitution reactions of haloarenes. I hope today's session was useful for you, beneficial for you. Thank you and have a nice day.